Good afternoon, everyone. Welcome to the Library Art Gallery. We have a new exhibition tomorrow. There's a few pictures up here to keep us company, but otherwise there'll be new paintings adoring the walls shortly. Welcome to the last of the Library Lunchtime Lectures for this semester. Our speaker today, Dr. Hüseyin Boyacı from the Psychology Department, will tell us all about reality constructed. How does the visual system work? Dr. Boyacı did his bachelor's, master's and doctoral degrees in physics at Bilkent University, and then he made the subtle transition into visual things relating to psychology when he went to his postdoc work in the US at New York University during the early 2000s, and then University of Minnesota. He then returned to Bilkent as a full-time member of the psychology department and was promoted to associate professor in 2013. His research areas include human visual perception using behavioral, computational, and neural imaging methods. He's published many papers, both more physics and psychology focused. You can see some of his papers exhibited upstairs, and his research has received grants and awards from various bodies, including Tubitak, Tuba, and the EU. I'm hoping that he is not a figment of our imagination, and that he is really here and not some visual trick. So let us put our hands together and welcome our speaker.
Thank you so much, David. Well, it's really a great honor to be here. I was just a little student like yesterday, and now I'm here and talking. It's really great. And message to my students, I want to see you here too. And before starting, I have to thank Aaron. Yes, thank you, Aaron, for postponing your talk unselfishly to next week, because somehow another talk was scheduled for the exact same time today with this similar topics. And to be honest, I would prefer to go to that talk. But I'm lucky I can be here. So that talk will be next week at this time, right? Okay. All right, so every time we open our eyes, like we did this morning, we very effortlessly see the world around us and very effortlessly recognize the objects, understand the scene. And moreover, this scene doesn't seem to change from the time when we went to bed, like yesterday, or the day before yesterday. And for all the time, for that matter, things seem to be like remaining the same. They don't seem to change appearance from night to day, from a sunny day to a rainy day. They remain constant. So these two facts, that we do it very easily and effortlessly, and that what we perceive, what we recognize, don't seem to change, make us firmly believe that what is actually out there, the physical thing, is what we perceive. We don't even consider the possibility of an alternative. We see it and we believe it. There can't be any other option. But reality is pretty elusive. Ask a physicist, what is this? There will be an explanation for this in many different levels. And indeed, we operate only at one level. Our sensory system has limitations. I want to show you a video clip here.
Looks like an ordinary city. But books can be deceiving. All of us are surrounded by things we can't see. Things that are too fast, too slow, too small, are simply invisible. But that is about to change. National Geographic takes you on an extraordinary journey into these unseen worlds. See where exciting new discoveries are taking us, and who or what we might meet along the way. uncover the mystery of things you didn't even know existed. And yet, are right in front of your eyes. Mysteries of the unseen world. Your world will never be the same. Coming soon to this theater.
Yes, it's coming here. I want to show you another video. This is a little bit more scientific. So what you see here is actually light traveling inside a bottle. This is called femtosecond photographing. So they took the picture of light traveling inside a bottle which is filled with some liquid. So we can see none of these things, right? So without any aid, our visual system doesn't have the capacity to see very fine details, doesn't have the capacity to see fast movements, and also the slow movements too, right? But, well, you can say, this is too artificial. You can snub this. You can say you're dealing with things that are not really relevant. And in fact, to a large extent, you would be right. So all these things are not really necessary for our survival in the environment. We don't need to see this much detail. For me, knowing that this wall is rigid and it's impenetrable by me is enough. I don't have to see the molecular structure of this wall, right? Because I cannot go through it. I don't have to see things behind it either. So how our visual system evolved depends on how fit we are for the environment. And another limitation of our visual system is the part of the electromagnetic waves or electromagnetic spectrum that we can see. So we cannot see the entire spectrum. We see just a tiny portion of this spectrum. Again, that's not an accident, right? Because many of the other electromagnetic waves cannot penetrate through the atmosphere. They are not around us. So being able to see them would not be really useful for us. It is useful for Superman, he has X-ray eyes, but it's not so useful for us. So we didn't need to evolve that capacity. Now, within this limited band of electromagnetic waves, we can discriminate different compositions of wavelengths. And how do we do it? By perceiving those wavelengths as color. So color actually exists only in our awareness, in our mind. The light waves and the photons don't have color. They have only energy, right? They have certain frequencies, certain energy, and the impression of that on us is color. And what a beautiful impression it is, and such a useful thing. It helps us detect objects. Like there is food here. If we didn't have color perception, if we had just grayscale perception, it would be so hard to detect our food. It helps us to recognize stuff. So it's much easier to recognize that this is a banana in this picture. It's harder to recognize that this is a banana in the other picture. Well, it provides social cues. So this is a baboon butt. Apparently, at the time when they are ready for mating, their butts turn red. Maybe my face is turning red now too. That's another social cue. So for social cues also we use color. And probably above all, it is beautiful, right? A sunset in full color is something that you cannot replace with anything else in life. Okay, so what is color? Like I said, color is the impression of different wavelengths on us. So different objects reflect different spectrum of light. Like a nice Ayash tomato reflects like long wavelength light, so it looks red. A blue pigment reflects more short wavelength, so it looks blue. And how come can we perceive all these? We can perceive all these because we have 3 different types of photoreceptors in our eyes. And those 3 photoreceptors respond to slightly different parts of the electromagnetic spectrum. For engineers, you can think this as basis functions, and with these basis functions, you can construct different functions on this side. And it turns out to be this distribution of basis functions is pretty accurate for like, identifying different wavelengths in nature. But not all animals have the same sensitivity. For example, this is the sensitivity of a honeybee. And how does the honeybee see the world? So this picture would be what we see in this flower. So it's a nice pattern. But there is actually a hidden pattern in this flower. And to be able to see that hidden flower, you have to have ultraviolet vision, which the bee has. So in the reality of the bee, this is the pattern of the flower. In the reality of human, this is the reality of the environment. So here we go. Reality is constructed. And that construction really is limited by our sensory organs. Now, where are those photoreceptors? They are at the back of our eye. That place we call the retina. And the retina is full of photoreceptors. Now, those photoreceptors which can discriminate between color are called cones. There's another class of photoreceptors, and that class is called the rods. Now, rods don't have subclasses like the cones, so they cannot see color. But they have better sensitivity at dark environments. So at night or in a dark place, our rods help us to see the objects around. But then we lose the ability to see the colors. And that's why the saying goes, all cats look gray in dark, because there is no color. Now, the retina is not a very simple structure, and we still didn't understand it completely. There is about 80 different types of cells in the retina. Many of them we understood how they work, but most of them we still don't know how they work. And already in the retina, there's a good deal of computation going on. So the output of the photoreceptors go to a layer in which there are those pooling of information, subtraction, addition, etc., and all these things. And in the end, what retina sends to the brain is not actually the stimulus that falls on the retina. It has already gone through some processing, and the images that the retina sends to the brain can be depicted like this, like low spatial resolution black and white image, higher spatial resolution black and white image, blue and yellow images, red and green images. Imagine them like that. So the rest, the brain has to take care of. And the first step that information goes to is a subcortical area called lateral geniculate nucleus, LGN. And after that, to the back of our head. First, to the primary visual cortex. So that's the entrance point to the cortex. From there, higher visual areas. And the areas, including LGN, all have layered structure. Different layers take different output of the retina. Like some of them take black and white, some of them take colored, etc. And they are all connected to each other. And also there is, again, a lot of feedback connection between the cortex and subcortical areas. Now, this is the hardest slide of the talk. Now, I'm gonna be honest. So before preparing these slides, I asked my students, what are the most interesting things you learned this year in this course? And they named a few things. One of them was this columnar structure of the visual cortex. So I have to explain it, although it's a bit difficult. Now, in the visual cortex, primary visual cortex, there is an amazing organization. It's a very neat organization. First thing is that if you go and look at any neuron in the primary visual cortex, you will see that it receives input from a certain part of the retina. And that certain part of the retina is called the receptive field. So that part is that neuron's receptive field. Now, if you go and investigate the next neuron, the neighbor neuron, where is its receptive field? It turns out that its receptive field is next to the receptive field of the other neuron. Okay, so neighboring neurons have neighboring receptive fields in the retina. This is called retinotopic mapping. Okay, and then different neurons are tuned to different orientations of bars, as you see here. For example, a neuron can be sensitive to vertical bars, another neuron to horizontal bars, another neuron 45-degree tilted bars. And where are they? They are not also arbitrarily distributed in the cortex. If we go and look, they are all neighbor. So if the neuron here has 90-degree preference, the neuron next to it may have 80-degree preference, and so on and so forth. And they are organized in columns. These columns are perpendicular to the surface of the cortex. And when you look from above to the cortex, you see a pinwheel structure like this. Okay, after primary visual cortex, what happens? After primary visual cortex, information is sent to different higher level visual areas. Some of them go in this direction. We call this the ventral pathway. So it's the bottom of our brain. Some of them go to the top of our brain. We call that the dorsal pathway. And the ventral pathway is usually involved with recognizing objects, understanding their form, their color, so on and so forth. And the dorsal pathway is usually involved with understanding the spatial properties of the scene, like scene, where the object is, how fast it is moving, so on and so forth. And according to classical models of vision, there is a one-way flow of information to a large extent. Things are processed in V1 and sent to higher levels, V2, V4, etc., or here, MT, etc. And there is little feedback in classical models. So earlier parts of the visual hierarchy is more the activity of earlier parts is closer to what is on the retina, physical properties of the image on the retina, and higher areas are closer to what we perceive. So that is the picture in the classical view. Now you will say, wait a minute, if everything is segregated like this, retina is sending 20 different images, and then after primary visual cortex things go up, down, etc. How come I am seeing a red ball moving, right? In our visual experience, there is a red ball moving. We don't see a shapeless color or a colorless shape or things like that. We see things combined. Like in the end, in our consciousness, in our perceptual experience, there is a red ball moving. How is this possible? So all these information processed in separate pathways should be put together again. And that is one of the big problems of visual perception today, and it's called the binding problem. And we don't know how it is done. But what we know is that attention has a significant role on this. Without attention, it turns out that different features are not bound together. In this classical experiment in 1982, researchers asked observers, like they showed this kind of stimulus very briefly to observers and asked them to, for example, sum these two numbers. So that was the task of the observer. I show you this image and ask you what is the sum of those two numbers. Okay, people are successfully doing that task, but after the task, they ask them what else they saw in the picture. And the answers are funny. They say they saw a red circle or a yellow triangle. So they misbound the features of objects. Why? Because attention was taken away from those objects. When they did the same experiment without the arithmetic task, they could just see the scene. They didn't do those mistakes anymore. Now, attention seems to be important not only for binding. Now, first of all, think of this. Why do we need attention? Constantly, we are bombarded with almost infinite amount of sensory information. At this point, you're listening to me, but actually, your sensory organs are receiving many input. You're able to ignore them. You are able to direct your focus to me. And that is possible because of attentional mechanisms. And there are examples which dramatically show importance of attention. This is a classic experiment from 1999. In this experiment, they showed people video clips of players playing basketball and passing the ball to each other. There were two teams of players, one in white shirt, one in black shirt. And the task in the experiment was to count the number of passes that, say, the white team does. But in the middle of the video clip, a gorilla entered the scene. Not a real gorilla, but a person who is dressed as a gorilla entered the scene from the right, walked to the middle, pounced its chest, stayed there about 30 seconds, and moved again and left the scene from the left. Now, at the end of the experiment, they asked, how many passes did you count? 15. No, it was 16. Okay. But did you notice anything interesting, weird in this scene? And believe it or not, 50% of people didn't see gorilla. The other 50% of the people couldn't believe that other people couldn't see the gorilla. But what is even more interesting is that when they monitored the eye movements of people, those who didn't see the gorilla looked at the gorilla for 30 seconds. They looked and they didn't see the gorilla. Here you go, that's reality again. So don't believe everything you see. Okay, now let's say the visual system did everything perfectly. Leave aside the sensory limitations. Within its sensory limitations, we solved the binding problem, we solved the attention problem, and everything. We are still left with a problem, which is the ambiguity problem. What you see, what you receive in the back of your retina is a two-dimensional projection of the three-dimensional world. Now imagine that this is the image on the retina. Does it come from this object? It could be, but it could also come from this object. It's pure geometry. So there is no unique answer to this question. What caused this image on my retina? Unless you use other cues that are present in the scene. Without other cues present in the scene, this is an unsolvable problem. It doesn't have a unique solution. And indeed, without extra information, extra cues, we often fail to see the correct object in the real world. Now, to most people, this looks like a globe, three-dimensional globe, put on a sidewalk. Maybe some of you know this street artist. But the actual picture is quite different. He painted this on the sidewalk so that from a certain viewpoint it would look like a globe. Why do we see that? Because of the ambiguity in the picture. We weren't there, we didn't take the photograph, we cannot move our head and see the correct shape of the object, so we failed to recognize the correct shape. Probably the visual system thinks that the most likely object in the world to explain this image on my retina is a three-dimensional globe there. This is a very unlikely thing that this cannot happen, unless I see it. When I see it, I say, ah, it's that, okay, I accept it. And look at this. That's unbelievable. From another viewpoint, it's this. So this is the ambiguity of the form. Is this the picture of a giant plane very far away from us? Or is it a little drone nearby? It's impossible to tell, unless you're a drone expert and you know from the tails, etc., oh, this is such and such drone, I recognize it, it is small. Or you're an aeroplane expert, you recognize this airplane. Now that happened to Homer too.
Searching for me with that giant helicopter in the distance.
It's not giant, that's not the distance. It's more
So the Predator drone wasn't really a giant helicopter in the distance. It was small and it was in their room. So in these examples, I showed you like the kind of failures of the visual system. But these conditions were deprived from many cues. Under normal conditions, in our rich environment where there are lots of cues, we don't make those mistakes. For example, this woman and this man seem to be pretty much of same height. They don't look weird, they don't look different. But actually, if you look at the image size of the guy, it's much smaller than the woman's image. So even though the image size of these people are on our retina are pretty different, we still perceive them of same height. This is called size constancy. So we can determine the size or guess the size of objects in the real world pretty constantly. Now I'm going to show some experiments, but before showing them, I need to show a technique called neuroimaging, Fmri. And with Fmri, we can actually take pictures of human brain, functional pictures of human brain, while they are watching things. In this case, they are watching moving dots or flickering checkerboard patterns. I'm going to stop this. It may make some people nauseous, those flickering checkerboard patterns. I'll continue showing on this one. So when we show moving patterns, we see that these parts of the human brain are active. When we show flickering checkerboard patterns, these parts of the brain are active. So using this neuroimaging method, we can show human observers some stimuli and then record their brain activity. So we can understand which stimulus cause what kind of activity and in which area of the brain. We can do, for example, those retinotopic mapping experiments. When this ring flickers, we find an activity in this region. If the flickering ring becomes smaller, by the way, the eyes are constantly fixated at the central mark. If the ring is smaller, the activity pattern will move to the back of our head. If the ring is larger, the activity pattern will move to the further front of our head, our brain. And this is not the only thing that people do with functional magnetic resonance imaging. So what I showed you is a relation between what people see and the activity that it causes. But people started to do the reverse. They look at the brain activity of people and guess what they were seeing. This is called brain decoding. And here's a video clip of this. So people are presented with this stimulus, and the machine learning system, after learning the brain activity patterns, comes up with this explanation for what the person was seeing. You see, especially with faces, the results are dramatic. And note, this is only from 2011. 4 or 5 years has passed over it, and the technology improved much more. Now, that may be a scary thought for some people. The ethical issues are, of course, need to be debated, because is it correct to look into the brain of people and decode what they were thinking? But those things aside, that's the state of the art of the method. Now, in our experiment, we showed people stimuli like this: a ring in the front, a ring in the back. Now, those rings have actually the same retinal size. But to people, on the average, the one in the back appears 16% larger than the one in the front. Why? Because of the perspective cues present in the scene. Now, we collected data while they were looking at this ring and while they were looking at this ring. Now, remember retinotopic mapping. If the ring is here, what we expect an activity here. If the ring is smaller, we expect an activity further in the back. If the ring is larger, an activity further in the front. Now, question is this: given that these two rings have identical retinal sizes, are they going to activate the same areas in the cortex? Or, because they are perceived to have different size, are they going to activate different parts of the visual cortex? And the answer is the second. They activate different parts of the cortex. The red patch corresponds to the activity to the ring that was perceived further and larger. The green one corresponds to the ring that is perceived closer and smaller. And just like they were real different rings, the activity that they created were also different. And this shift in the pattern of activity was consistent with the perceptual effect. And that showed that the activity in primary visual cortex correlate with perceived size of objects, not the retinal size. And this came as a big challenge to classical models of vision, because classical models of vision thinks that there's a strict fixed retinotopic mapping between retina and the visual cortex. And probably for the first time, this experiment showed that that's not always the case. So that can be violated. And by the way, I didn't show you, but attention had an effect on the results too. Now, ambiguity is not only in the form. There's ambiguity also in color of objects. Now, let's think what the visual system is trying to do. The visual system is trying to find the reflectance of the object. Is this tomato red enough? Should I buy it? Or is it a bit greenish? Now, the light reflecting from the surface of the tomato doesn't depend only on its reflectance properties. It also depends on the illumination. But how can we do that? Because all we have in the eye is the luminance coming from the object. From that, we have to solve an equation which has multiple unknowns. So one equation, many unknowns. Again, an ambiguity. And indeed, without any cues present, you would expect that humans should fail in judging color of objects. Now, an example. Here is a moon on a clear night. What is the color of moon? Astrophysicists can keep quiet. So is it black? Is it mid-gray? Is it white? Is it light gray? What is the color of moon? Any ideas?
Light gray.
You knew it. Dark gray or light gray?
Light gray.
Light. Okay. Okay, you didn't know. So, good. Well, the average reflectance of moon is just 8%. It's pretty dark gray. It's not even gray, it is very dark gray. And actually there was a recent photo from a NASA camera, took a picture from 1 million miles away, during which moon was crossing the face of Earth. And here you can better appreciate the color of the moon. In this one, you can't, because there is no cue around it. There is nothing to tell you what actual color of this object is. There is only the luminance of light that is reaching your eyes. Here, checker A, checker B. Checker A looks darker than checker B. Right? This looks like dark gray, this looks like light gray. Very well. That is good. That is really actually their actual colors. But in fact, they have identical luminances coming to your eye. You see, I just cut and copied it. Now, if your question to the person is, tell me, what is the luminance of light coming from those checks? This is an error. So the person is making an error when they say these have different colors or different brightnesses. But actually, this is a success of the visual system, because the visual system can appreciate the complexity of the scene, can appreciate that there is light coming from this direction, and a shadow is cast here. So because this is in a darker environment, okay, if the same amount of light is coming from both A and B, then B must be a lighter surface. Doing that, inverse optics solution, it comes up with the answer. B is lighter. So that, from that point of view, this is a success. From the point of view of telling retinal luminance, it is a failure. But in my opinion, because whatever is on the retina is not so relevant for our fitness in the environment, for us what is important is the actual color of objects. This is a success of the visual system. Well, this is my demo. Here, those two balls appear to have different colors to most observers, I believe. So this looks like bluish, this looks like reddish, but actually they are both gray, just gray, and same gray. But one of them seems to be illuminated under my broken IKEA lamp with yellow color, the other one with blue light. So because of that, the visual system makes inverse optics again, maybe, we don't exactly know that. Thinks that this is a blue surface and this is a red surface. Now I showed you some types of color perception experiments, and I want to show you a color constancy example. So this orange looks like orange, color orange, in this picture, and in this picture too. But if you cut a piece of this orange and move it here, it would actually look green. So even though the light reaching from those objects are very different, we still perceive oranges as in orange color. And this is called color constancy. Now I'm running out of time, so I will skip this experiment and show you a final example and go to the conclusions. Now what do you see here? Pac-Man. What do you see here? What do you see here? Pac-Man. 3 Pac-Man. You saw 3 Pac-Man until now. Now what do you see? You see. So my students know. Now you see a triangle. But wait, there were 3 Pac-Mans. Where did they go? They are still there. Why don't I see 3 Pac-Mans here? Well, we don't see because probably a triangle floating in the space in front of 3 disks is a better explanation of this scene. It's a more likely explanation of this scene. Therefore, the visual system prefers that explanation. It's an inference. it infers from the ambiguous retinal image what the actual object out there is. Now, Gestalt psychologists called this the whole is different than the sum of its parts. Well, they said actually more than the sum of its parts. But I changed it slightly to say different than its parts. Translation for engineers, the system is nonlinear. 1 + 1 doesn't make 2. And that's our problem when we try to understand the visual system. It's a very difficult problem. And in general, when we try to understand the brain is such an immensely nonlinear system. That's why it's taking us so long to fully understand it. And it will take even longer. Okay, so to my conclusions. I've been saying these things all the way up to now, so I'll just read them. The visual system doesn't seem to be primarily interested what is on the retina, right? So like its retinal size or retinal luminance. Instead, it has evolved to estimate invariant properties of the objects around us, like their intrinsic properties such as actual size, real velocity, and surface color. Like these are more important for us. What is physical what is physically real in the real world, like subatomic things, etc., or what is actually on the retina, are really not relevant for our survival, right? For our survival, what is important is invariance and how to interact those invariant objects. That is the important thing. So evolution doesn't favor veridicality, like realness. Evolution favors fitness in this environment. And for fitness, we should be able to recognize those invariant properties of objects. Now, what are our problems in vision? Well, the big problem, from ambiguous retinal image, how do we get to this perception? But that's a huge problem. There are sub-problems that we couldn't solve yet, so there are pieces of puzzle still missing. We still need to better understand neurons at molecular and cellular level. We don't have a complete understanding of that. We need to understand the connectivity patterns within and between brain areas, including those interhemispheric interactions, right? We have two hemispheres connected through corpus callosum. How those two hemispheres interact with each other. Feedback and feed-forward connections, how do they work? We need to still better understand the effects of attention, effect of context on visual processing. We need to understand combining cues that are in the environment, cue combination, binding problem. And from the model and theory side, we are very, very poor at the moment. We don't have good unifying models, theories to explain vision or the brain. We need that. Currently, popular models include statistical models like Bayesian inference models, things that optimize gain. For example, if it is dark and at night, if you hear something creepy and you see a shadow, it might be better to run away, even if it is not likely to be like a predator. But the risks are so large, if it's a predator, your life is in danger. So you have to consider this also. You have to consider optimizing your gains. Predictive coding models, which treats the whole brain as a prediction machine, predicting what will come every moment as a next step. Empirical models, deep learning nets, inverse optic models. Can't go into detail in all of them. And these are popular models. What are we doing recently in the lab? Just 1 minute. We look at contextual effects on contrast perception under leadership of Zahide. Temporal dynamics of cortical processing in brightness illusion with Can and Zahide again. Here the idea is if we can look at high temporal resolution, we can better understand connectivity patterns between brain areas. Buse is trying to test predictive coding predictions in experiments. and Esra is looking at brain activity in people with uncorrected vision. Oh, why study vision? Okay. Well, because of curiosity, right? We have this capacity to see. We are curious. Primates are curious, so we have to know it. Like if we are interested in the Big Bang and expansion of the universe, we are also interested in how our brain works. It's a model system to understand the brain because you can study the activity of the brain very systematically. You can give a certain amount of luminance to the eye and look at the activity. Certain size of object, look at the activity. Other modalities are not that suitable, are not suitable for systematic studying. Well, why study brain? Of course, for health, robotics and AI, education, and all aspects of human life. 15 seconds, support. I'm very grateful, of course, to my institutions, Bilkent University and MR Center in Bilkent. Without their support, nothing would be possible. And external supports coming from TÜBİTAK, TÜBA, and European Union. Well, thank you very much for your patience.